Today we're going to discuss Dedekind Cuts. Let's do a brief recap from last time. Let's say that we have an ordered field F, and let's let A and B be subsets. We'll say that an element lowercase b is an upper bound for our set A if b is greater than or equal to x for all x in our set A. Similarly, I'll say that an element lowercase b is a lower bound for the set B if b is less than or equal to x for all x in our set B. An element S is said to be a least upper bound for the set A if two things happen. 1. S is an upper bound for the set A, and 2. S is less than or equal to B for any other upper bound B for the set A. We'll denote S as sup A, called the supremum of capital A. Similarly, we'll say that an element S is a greatest lower bound for B if two things happen. 1. S is a lower bound for the set B, and 2. S is greater than or equal to B for any other lower bound for our set B. We'll denote S as INF of B, called the infimum of the set B. We'll say that our order field is complete if the following property holds. It's called the least upper bound property. Every non-empty subset capital A that has an upper bound has a least upper bound. Equivalently, we have the greatest lower bound property. That is, every non-empty subset which has a lower bound has a greatest lower bound. Infimums and supremums are related in a way that's shown here on the slide. Given a set capital A, we can construct a set capital B that just corresponds to the negatives of the elements in capital A. If this is the case, then the infimum of capital B is equal to the negative of the supremum of capital A. We have a property now that explains how we might be able to deal with the supremum and infimum in practice. Let's let A and B be non-empty subsets. If we assume that our set capital A has an upper bound, then for every positive element epsilon, there exists an element A sub epsilon in the set A such that A sub epsilon plus epsilon is greater than the supremum of the set A. In other words, we can get as close as we want to the supremum of capital A by looking at elements A sub epsilon in the set capital A. Similarly, assume that our set B has a lower bound. Then for every positive epsilon, there exists an element B sub epsilon in the set capital B such that B sub epsilon minus epsilon is less than the infimum of the set capital B. In other words, we can get as close to the infimum as we wish. The point is that we can always find elements B sub epsilon that get as close as we'd like to get to the infimum of the set B. Using all of this now, we can discuss the idea of a bounded set. Let's say that A is a subset of F. We'll say that an element lowercase a is a lower bound for the set capital A if A is less than or equal to x for all x in the set capital A. Similarly, we'll say that lowercase b is an upper bound for the set capital A if x is less than or equal to lowercase b for all x in the set capital A. We'll say that the set capital A is a bounded set if it has both an upper bound and a lower bound. Say that we have a sequence of elements x0, x1, x2, and so forth coming from the field F. We'll say that this is a bounded sequence if the set containing these elements is itself a bounded set. Here's a different way to think of what it means to be a bounded set. We'll say that capital A is bounded if and only if we can find a non-negative element capital M such that the absolute value of x is less than or equal to m for all x in the set A. Now we'll introduce the concept of Dedekind Cuts. A quadruple, that is consisting of a field, addition plus, multiplication times, and an ordering, is considered to be a complete ordered field if the following 14 axioms hold. The first is closure. That is, given any two elements x and y in the field F, both the sum x plus y and the product x times y are in the field F. Second, we have commutativity. That is, the order in which we have our addition does not matter. X plus y equals y plus x for any x in F in capital F. Next, we have associativity. Given any three elements x, y, and z, we could first add x plus y, then add z, or we could add y plus z, then add x. Next, we have the existence of an additive identity. That is, there exists an element that we'll call 0, satisfying x plus 0 is x for all elements x. Next, we have additive inverse. That is, given an element x, there should exist a negative x such that x plus negative x is the additive identity 0. Next, we have commutativity for multiplication. That is, x times y is y times x for all elements x and y. Next, we have associativity. That is, first we can multiply x times y, then multiply times z, or we could multiply y times z, then multiply times x. We have the existence of a multiplicative identity that will denote by the number 1. That is, there exists a number 1 such that x times 1 is x for all elements x. We have multiplicative inverses. For every non-zero x, there exists an x to the minus 1 such that x times x to the minus 1 is our multiplicative identity 1. Then we have distributivity. This relates addition and multiplication. Given any three elements x, y, and z, we could first add y and z and then multiply by x, or we could multiply x and y, multiply x and z, and add those two together. We have three properties that correspond to the ordering. First, we have the trichotomy property. Any element x falls into one of three categories. Either x is 0, x is greater than 0, or x is negative 0, less than 0. Second, we have if any two elements x and y are positive, their sum is positive. And if any two elements x and y are positive, their product is positive. Finally, we have the least upper bound property. That is, every non-empty subset A of our field F that has an upper bound B has a least upper bound C. Our goal for today is to explain how to construct the real numbers as a complete ordered field by considering the rational numbers. To this end, let's say that we have any ordered field F. We'll explain how to construct a complete ordered field using this. A subset of an ordered field is called a Dedekind cut if it satisfies the following four properties. First, it should be non-empty and proper. That is, our subset A should not be equal to the empty set. It should have at least one element. And A should not equal to the entire field F. That is, there should be an element of F that is not in A. Second, our set should be closed downwards. That means the following. Given an x in F that satisfies x less than A for some element lowercase a in capital A, then this element x must be in the subset A. Third, our set has no greatest element. That means, given any element lowercase a in our set capital A, we can find an element C in our set capital A such that A is less than C. For example, when F is equal to Q, we know that we have an ordered field. Let's take a look at all subsets of Q. We can fancily write this as A is an element of the power set of Q. All such subsets that are Dedekind cuts will be called a real number, and the collection of all such will be called R. Eventually, we're going to prove the following. R is a field which is ordered and complete. This will be a slightly strange construction because the elements of R themselves are sets. They're Dedekind cuts, but they're still sets. So we have to do a little bit of work to define addition, multiplication, and an ordering in order to prove that all of this is going to work. Let's first talk about some examples and non-examples before we go any further. Fix a rational number R and consider a subset A that's the set of all rational numbers x less than R. You can think of these as all of the rational numbers to the left of the given rational number R. We claim that this subset is a Dedekind cut. The intuition here is that you can divide the rational numbers into two regions, everything to the left of R, what we're calling here A, and everything to the right of R. On the screen here, we're calling this A tilde. So the idea is that we can think of the rational numbers Q as being cut in half at this rational number R. Namely, we have the set A and the set A tilde. For this reason, we're going to identify any rational number R with the Dedekind cut A. So in this way, we'll think of the rational numbers as being contained in the real numbers. We can generalize this slightly. For any positive rational number R, let's consider the following subset A. This will be the collection of rational numbers x, such that either x is negative or x squared is less than R. We'll claim that this is also a Dedekind cut. The intuition here is that we've cut now the rational numbers at the square root of R. So everything to the left of the square root of R is what we're calling our set A, and everything to the right of this square root of R we can call here, as we do on the screen, A tilde. Notice that intuitively the supremum of A is the square root of R, but this only exists when R itself is a perfect square. So here we'll identify the square root of R with this Dedekind cut A. And here the square root of R does exist as a real number whenever R is a positive rational number. Notice that the empty set and all of Q itself are not Dedekind cuts. Again, a Dedekind cut must be non-empty and it must be proper. Since the empty set and all of the rational numbers are empty and not proper, they cannot be Dedekind cuts. Any bounded interval from A to B is not a Dedekind cut. The idea here is that a Dedekind cut must be closed downwards. For example, if we consider the interval, capital A, that consists of rational numbers x between lowercase a and lowercase b, then we'll see here that lowercase a is to the left of everything in our set capital A, yet this lowercase a is not an element of the set capital A. Hence, this set capital A is not closed downwards. Finally, let's consider a rational number R and the subset capital A, which consists of rational numbers x, such that x is less than or equal to R. Earlier, we took a look at the set x is less than R and saw that it was a Dedekind cut. Now when we say x is less than or equal to R, this is not a Dedekind cut. Indeed, the problem here is that a Dedekind cut cannot have a greatest element. We'll see here that if we were to choose A is equal to R, this is an element of our set capital A, where we cannot find an element lowercase c such that A is less than C. Again, this set here does have a greatest element, therefore this set cannot be a Dedekind cut. Now let's try to make some definitions here that will turn our collection of Dedekind cuts into a complete ordered field. Given two Dedekind cuts, capital A and capital B, let's make the following definitions. First, we'll define the sum and negation in the way that you see here on the screen. It's a rather awkward definition, but we'll explain why on the next slide we're making these choices. We can also define an ordering on the collection of Dedekind cuts. We'll say that A is less than B whenever A does not equal to B and A is contained in B. There's some other equivalent definitions using this, what we're calling square bracket 0, which just consists of the elements to the left of 0. Here we can say A is less than B precisely when B minus A is greater than 0. What we mean is B plus the opposite of A contains this square bracket O. Finally, we can define the product and inverses in a rather strange way that we have here in the slide. We want to be very careful to keep track of the ordering. Remember that we had one of the properties that the product of two positive numbers should itself be a positive number. In this case, let's say that A and B are two Dedekind cuts that are greater than our square bracket 0. What this means intuitively is that both A and B contain all of the negative elements, that is, all of the Z and F that are less than 0. Then the product A times B should be positive, meaning that it should also contain all of the negative elements. Similarly, for the inverse of B, it should contain all of the elements that are negative, all of the Z less than 0. Once we define the product A times B and even the inverse B to the minus 1 for those positive Dedekind cuts, we can then extend to all possible Dedekind cuts just by thinking a little bit about the various signs. For example, if A is negative, then the negation of A should be positive. And then we can just use the various properties. Here's a slide that explains how this is related to what we expect to happen. Let's choose two elements R and S from our field F. We'll denote capital A as square bracket R, that is the set of elements to the left of R, and let's denote our set B as square bracket S, that is, these are the elements to the left of S. We'll see that both examples are Dedekind cuts. Also, the sum A plus B is just square bracket R plus S, whereas the negation negative B is the square bracket negative S. So this really means if we think of an element R as the same thing as the Dedekind cut square bracket R, then addition and negation make intuitive sense. The ordering here also makes sense. One can show that A less than B if and only if R less than S. So again, the ordering that we have from the field F corresponds exactly to the ordering that we defined on the previous slide. Finally, for the product, A times B will be equal to the square bracket of R times S. So again, multiplication in F corresponds to the strange definition of multiplication that we gave for these Dedekind cuts. Putting all of this together, we have our big result. If we're given an ordered field F, let's consider script F the collection of all Dedekind cuts coming from this field F. First, we have a map that will take an element R from our field F and construct the Dedekind cut square bracket R as at the top of the slide here. This allows us to think of our ordered field capital F as a subset of this script F. Finally, the big result is that this script F is a complete ordered field. That is, the script F satisfies all 14 axioms that we saw on the previous slides. When F is equal to Q, then script F here is just what we call the real numbers. In particular, this theorem actually shows that the real numbers is a complete ordered field, and the rational numbers is just the subfield. Actually, what's very nice about this construction is that even if we were to choose F to be the real numbers, and then do this construction all over again, we would actually find that script F is just equal to the real numbers all over again. Thanks very much for listening.